maybe we will focus on one very important statement, which is the name of the general frame is the Gelfand-Dickey approach. Decay. So all what I'm talking about now. The principal statement will be the following: that so if we consider this technique to find the just one branch of the square root of the differential operator of this type, we can define all operators of such type, pseudo-differential operator of such type. Okay, so it is just L1 over 2 multiplied by Ln. They should commute, so it is not a question from which side you multiplied the square root by the power Ln. And when we define several operators, several projections on the space of pseudo-differential operators. So first of all, if some b is the sum of from minus infinity to n b I d I, then b plus is the sum from e from 0 to n bi di, and b minus is the rest. So it's the sum from I minus infinity to minus 1 bi di. And I will also need a notion of the residue of a pseudo-differential operator. Residue of b is b minus 1. It will play a very important role.
They are complex operators.
Complex, what do you mean?
I don't know.
B are functions. B are rapidly decreasing function on x. Bi are rapidly decreasing function on variable x. Real, for example, real. Okay. And we consider a pseudo-differential operator because we have negative powers of d. But all coefficients are rapidly decreasing function on x.
Is the rest of d?
Yes. The residue of this pseudo-differential residue, and it is minus 1 coefficient of this series. It is very important. So the residue of a pseudo-differential operator is its minus 1 coefficient, which is a function on x.
That's what I mean when I say complex, because that's the Laurent series. That's the Laurent.
Yes, if you like.
The minus 1 term is the residue. Yeah.
Yeah.
So they have to be in complex space.
No, it's from different point of view.
Now
Yeah.
it's only mean the coefficient of that term.
Let me write you a lemma, which is very important. If you consider residue lemma, residue of b of the commutator of two b and c is always a function h prime. For some function f from our space of rapidly decreasing functions on x. So it's a derivative, and it means that integral of residue of the commutator x is 0. So I will not spend our time on, but it will be the whole task 1. And it can be found in the book of Dickey. How it is called? Hamiltonian structures. Structures in soliton equations. So the initial step are done. So we need this decomposition, projection to the positive and negative part, and this coefficient will be also important in one consideration. Theorem. The flows L dt n of L equal to L to n plus 1 over 2 plus L commute with this L. And the first non-trivial one, the first dt1 of L, which is L 3 over 2 plus L, is the KdV equation. Let us calculate something. For example, what is L 3 2? L32, it is L1 over 2 multiplied by L. Do you remember what is the L1, 2? It is D minus 2U, D minus 1, like this. Do you remember? Plus, etc. I think we need some more terms. Let us try to start to calculate. We will see if we need more terms in this expansion. So we have to apply, we have to multiply L1 over 2 by L. We multiply this, and then to take the positive part, non-negative part. So we multiply this by d squared plus u, and this is d power 3 minus 2u d power 1. This with this, okay. And then when we multiply this by this, we get minus 2 u prime ux. And if I understood, it is all the non-negative part. After this, we get the rest, but the rest no. Here we could get some other term. So we need to calculate the next term. D minus 2u d minus 1 plus w d minus 2. So here we get plus w by this term, just by multiplication. And here we get minus 2u square d minus 1, etc. So the rest is negative, but this is the non-negative part. So could we calculate this coefficient? And I have notes there. This is not 2u, but u over 2. Let us verify. Let us calculate for two first terms in the square root of L. Yes, it is u over 2 because we have two. We had 2b1 equal u. You remember? So we have the square root, which is d plus b1 d minus 1 plus b2 d minus 2 plus etc. And we get 2b1 is equal u, something like this. So let us calculate this.
Well, this result for L.
Yeah, the square root. Yeah.
That's the square root expansion of the operator.
Yeah. Of a pseudo-differential operator. Yeah.
Yeah. Okay.
Okay, it will be else you home task. I will give you an answer, but you have to know how to verify it. B2 is minus no is ux over 4. Ux over 4 minus 1 x over 4. Yeah. So we have to place it here. And 1 over 2. And here 1 over 4 ux. And now, so we have to calculate this for, yes, this is the, this part is L 3 over 2 plus. And now we have to calculate this commutator. So my statement is that it is exactly the so it is exactly equal to u t1. So it's a differential operator, but it is of order 0. It contains only the part which is a multiplication by a function. All other part will disappear after this commutator, which is not trivial by the moment, because this is an operator of the order 3, this is an operator of the order 2, its commutator is an operator of order, of which order? In general. So if you commute two operators of order 3 and 2. No, 4. Because the principal term disappears. Okay? When you commute the principal terms, even in this type. So if you commute f dk and g dm, it is f g prime maybe k g prime minus m f prime d m plus k minus 1. Okay? So normally it's an operator of the order 4, but in fact it will be an operator of order 0. And it is quite simple to view. Let us over 2 plus commutator with L. Let me add and subtract here the minus part of this power. So it is plus L 3 over 2 minus L 3 over 2 minus, and commutator with L. Okay? This is just L. I will write it. This is L over 2 with L, just complete, minus L minus with L, but this is 0 because it's just the power of this operator, they commute. And this is a pseudo-differential operator of order. This is an operator of order minus 1. It is of order 2. It is a pseudo-differential operator of order 0. Differential operator of order 0. But you know that this is a differential operator. So this play with positive and negative part here is very efficient in many questions. So you see, we calculate something strange, but it appears a differential operator of order 0. So it is just some derivation. So it is LT1 dt1 of L. So it should be a differential operator of order 0, and it does. Okay. So this will be your home task too, to verify that this commutator is exactly the KdV equation on the function u. I would like to proceed to the commutation condition of different flows, and it is very beautiful algebraic stuff, which can be applied in many different situations. So what theorem? Not theorem. It's the same theorem. So the first, the one part of this theorem with these comments on commutations of these operators. So it makes possible to compare left and right part, but exact comparison is your home task. Why they commute and why it is close to the integrability. So in integrable systems, in Liouville integrable systems, we have commuting Hamiltonians, and they correspond to commuting Hamiltonian vector flows. Okay, so these are flows. I would demonstrate that they commute, but in fact they will be Hamiltonian with the Hamiltonian structure I described, but it doesn't fit in our program of this semester. So we have just to calculate the following thing. We have to find two derivations. And we have to verify that it is the same as this one if we define it just by our formulas. So we have to verify this. Okay. Let us try to calculate. So this is dtn of the commutator of L 2m plus 1 over 2 plus with L minus this part dtm of L 2n plus 1 over 2 plus L. And okay, so what is it? There is differentiation of this part, so dtn of L 2m plus over 2 plus of L minus dtm of L 2n plus 1 over 2 plus with L plus L 2m plus 1 over 2 plus dtn of L. I will use our formula, so it will be L 2n plus 1 over 2 plus with L and the second commutator. So I apply this flow to this point. Okay, just a moment. Yes, and now I have to apply differentiation of Tm to this L. So it is L 2n plus 1 over 2 plus, and here it is L 2m plus 1 over 2 plus applied to L in the second commutator. So I'd like to expand in details the following expression: dtm of L 2m plus 1 over 2 plus minus dtm of L 2n plus 1 over 2 plus. So first of all, this differentiation and this projection, they could be changed. Okay? Because it's a linear operation. This projection is a linear operation on the space of pseudo-differential operators. Okay, so it's L2m plus 1 over 2 dtn of L2m plus 1 over 2 plus minus dtm L2n plus 1 over 2 also plus. Now I have so dtn of L is L 2n plus 1 over 2 plus to L. I have to calculate, to apply this to the power. So my statement is that dtn applied to L S is equal to L 2n plus 1 over 2 plus Ls. So that the application of this flow to the powers of L will be the same will be given by the same Lax representation. We have seen this, but we have seen this for integer s. Let us start by integer s. So if we apply this flow to the s power of L, integer s, it means that dtn of Ls is the sum of Li I from 0 to s minus 1, dtn of L and L s minus I minus 1. We did it just in an infinite number of times, so it's the same. But what is it? It is the sum from 0 to s minus 1, Li, and here we have to write, I will denote it by m. M, L, L, S minus I minus 1 minus Li, L, M, L, S minus I minus 1. Do you remember? And in this sum, all terms except the limit case cancel each other. So it is equal to M, L, S minus 1, Ls minus 1, no, not minus 1, S, just S, minus LSM. So this is true for integer s, and Dickey proposed the following way of reasoning for the fractional powers. So dtn of L1 over 2. It is something. It is just. It is something concrete. So it's a differential operator, and it should satisfy the following rule. It should satisfy the following rule that DTL, it is DTL power 2, and it should be ML and we can guess this operator. So if we write dtn L1 over 2 equal M L1 over 2, this will be satisfied. Okay? And if you understand that it is unique, that this is some unique pseudo-differential operator, it should coincide with this. Okay? So I'd like to write this formula, to use this formula now for all S. S is 2m plus 1 over 2. Because it is true for integer powers of L, and for fractional powers which are which has denominator 2. Okay, so in this formula, I have to. I'm sorry, I stopped here, and so now I will use this formula. and this is L to n plus 1 over 2 plus L to m plus 1 over 2 plus minus L to m plus 1 over 2 plus L to n plus 1 over 2 commutator plus. And I have to prove that it is equal just to the commutator of pluses. So it is L to n plus 1 over 2 plus. This is the complete L, so I can write it as L to m over 2 plus this plus is not necessary, but I have to write else L minus plus L to n plus 1 over 2 plus L to m plus 1 over 2 minus commutator plus minus plus minus minus plus minus and minus L to m plus 1 over 2 plus L to n plus 1 over 2 plus. Okay, to this form I can add L to n plus 1 over 2 minus L to m plus 1 over 2 minus plus. This is 0 because it's a commutator of negative part of operators, and we get the positive non-negative part of the commutator. This is 0. So I can just add this to this form, and then I add it. I can subtract this plus, because the sum of positive and negative part of this. And here I have something very strange. Not strange, because I have to change the order. So it is this is equivalent to plus L to n plus 1 over 2, L to m plus 1 over 2 plus. And this is L to n plus 1 over 2 with L to m plus 1 over 2 without signs, commutator and plus. But just the powers commute, the powers of L commute. The plus and negative part doesn't commute in general. But here are just the powers of the same differential operator. It is very close to the Adler-Kosten-Syme scheme, which we used in the description of the full symmetric Toda chain. Here, there is another projection to two parts of the algebra of pseudo-differential operators. But the powers, just the powers of L, commute because they are powers of L. Okay, so this is 0, and we get just this term, L to n plus 1 over 2 plus, L to m plus 1 over 2 plus. And what we get, so it was about this part of this expression. I will rewrite it now, or okay, I will. So I prefer to erase this line, and we will get here L to n plus 1 over 2 plus L 2m plus 1 over 2 plus commutator even without plus, because they are non-negative. But we have the commutator with L here, plus this form. And my statement that is a Jacobi identity. So it is 0 because it is just a Jacobi identity for 3 elements of this algebra of pseudo-differential operators, of differential operator, whatever. Okay? There is something very fundamental in this concept. We tried to calculate some maybe non-natural object, some projection of the differential operators, pseudo-differential operator, but it produced commuting flows on the space of differential operators now. You see? Even if the d-1 is not an operator which acts on functions, this algebraic concept allows to define commuting flows, commuting dynamical flows on the space of functions u, because we define a flow on the space of operators L, but in fact it's the same as the flow on coefficient q, which is a potential of the Schrödinger operator. Okay. Okay. What else? Just briefly. Conserved quantities. Conserved quantities. Conserved quantities. They should be functionals on our space of differential operators or on these particular potentials of the Schrödinger operator. So we have to define some functionals on this space. So the statement is the following, that we can define a functional jk which is an integral of residue of L to k plus 1 over 2 dx. And theorem are conserved quantities of all flows, of all defined flows. Remember, we have defined just a hierarchy of flows on our space of functions u. The first of them is the KdV flow, just the initial KdV equation, but we can define them all. Conserved quantities. So they are conserved along all our flows. How to demonstrate it? Just we apply dTm of gk is the integral of the residue of L to m plus 1 over 2 plus to L to k plus 1 over 2 dx. And you remember the lemma about the residue of the commutator of pseudo-differential operator. It is always exact it is always a function which is a derivative of some function. So this is a derivative dh over dx, and it is always a function from our space, from the space of fastly decreasing functions at infinity. So just this, I'm sorry, the residue of the commutator. So it means that it is zero. Moreover, these conserved quantities will be Hamiltonians of these flows in the Poisson bracket I have defined. But it's a huge and very interesting set of properties of this system, of this equation. I should mention else. What is called the inverse scattering method. But it's a story of the semestral course to study all this concept. But you see, the Lax representation for this problem means that some spectral properties of this operator are conserved. You understand? Like in the finite dimensional situation, if you have a finite dimensional integrable system, dynamical system, and you have the Lax representation of it, it means that the spectral curve or just the characteristic polynomial of this Lax operator is a conserved quantities at all this frame. Here, the Lax operator is a differential operator, but one can study its spectral properties. And the generic fact, even in a field theoretical situation, so if you study some field theory like this one, the spectral properties of this Lax operator are conserved quantities. So, and the inverse scattering method is based on the study of the spectral properties of the Schrödinger operator. And you understand that it is very deep and important subject in quantum mechanics and in many other physical problems. So it is related, the spectral theory of the Schrödinger operator is related to the KdV equation. I think we can stop now with the theoretical part. If you would like to discuss some home tasks or to make some exercises from this lecture, we have half an hour. What do you think? Okay, I propose now to demonstrate that the first flow with that L dot, which is L 3/2 plus with L, is the KdV equation. Let us do it now.
So the idea is to obtain the KdV equation from
Yes,
the
yes, to say that this equation is equivalent to the KdV equation.
Maybe I can give it a try.
Please try.
So if we take the this part, and we don't consider smaller terms, we can keep only this.
No, you see, we have to know this, because the multiplication of this with this gives the zeroth term.
Yes, but if we take only the positive part,
Positive it is non-negative
non-negative.
with zero part.
Yeah, you're right. Yeah, yeah, it's greater.
But it is not very different from what you need. Yeah. I don't understand. I don't understand what is from which, from what, where it comes, from what it comes.
These two, this. Yeah, it's this term with this term. Minus 2. Yeah. Okay. So we only have to consider the positive, so we don't consider these terms.
No.
Well, it is. But the idea is.
And this is d applied to this.
Yes.
The second. And this? From this?
No, it should be this to this. And this to this should have 3 1/2 u d minus u x over 4. See?
So this term, is it this applied to this?
Yes.
But there is another term. When you apply this to this,
Yes.
there is this part, and there is another part, which is 2 ux 1 over 2. But this 2 is from this ux, and the rest is d from this. Okay. D u is u d square plus 2 u prime d.
I see.
Okay? And that's all.
Yeah.
So you have to calculate this also. And in this case, it is 2 1 over 2 ux, and the rest is d at the first power with this d is equal. So there is this just this coefficient.
Okay, but this term, you get this term because you apply this in this relation.
It is better to think that you don't apply, but you multiply this differential operator, and this is an operator of multiplication by the function u. And then you multiply, you compose these operators, it is equal to this part. Is it clear or not?
No, it's not very clear.
If not, we have to apply this to a function f. So both of these are operators,
Yes.
and this is a function. So we apply differential operators to some function. And this is the same as you apply u at first, and then you apply differential. So it's d2 of u of f. And this is differentiated by parts. We forgot
Yes.
plus u prime. Yes. So this is u2 prime f plus 2 u prime f prime plus u f 2 primes.
Yeah, okay.
So it was my mistake.
Yeah. So the idea when we apply, when we have this,
Yeah.
is
Yes.
that,
Yes. We have applied.
so we have
Yeah.
to
Yeah.
put this right here.
Yeah.
Yeah. Okay.
So just a multiplication of operators of a differentiation and of multiplication by u.
I will put it first this way, and then I will substitute it.
Very good.
Okay, so this one should be.
Yes, yes. So it is just a multiplication, so it is associative.
Yeah.
Okay.
So yeah, so
Yes.
we can do this.
Yes, and we apply this formula. This.
Yeah. Should be. Well, it's the same thing, but now we have. We already have the first derivative.
Yes, but we apply the second derivative. And
Like this.
Mhm.
Okay, so now that the idea is that we have to take only the positive exponents of this result. Okay, so we don't take this part
no.
or this part.
Uh-huh.
Okay. So this is this and this is this. So we also don't take this
Mhm.
part, and we also here we are okay.
We multiply by d minus
Yeah, you multiply by
Mi-
by d minus
uh-huh.
1. Yeah.
minus
Right.
2. Minus 2. Uh-huh.
Yeah, minus 2. Yeah.
Minus 2. But this term,
Yeah, yeah. What you said, you have to conserve this term. Yeah.
mhm. Yeah, very good. Mhm.
Consider this. On the UX here, you yeah, this is the.
Mhm.
Okay, so now the rest is.
It's a little bit strange. So it's the same derivative.
Yeah,
Uh-huh.
you're right.
It's a little bit strange, but
no, I
we will see.
I
We will
forgot.
see.
I was
No,
using-
I'm not sure about the coefficient here. So it is 3 over
7/4. No, let me.
Ah.
It's
7 over.
7/4.
Yeah. It is strange. So yes, it's a little bit strange.
Yes, because we have to obtain 3/4.
Something like this. Let's calculate. We will see. But it is very close to what we need.
It's only the, So now we have to consider the partial derivative.
Yeah.
Of this.
Yeah.
But so here we should use the same idea. We should act this operator over the function, and in order to compute the
No. Now you consider an operator as a point in the space of operators,
Mhm.
and you consider its evolution. So you apply a flow to this differential operator. This part is not changed. So it is all only
You only have this
yes,
term.
yes. So this is a trivial term. So
Yeah.
let's start by this simple term, the commutator of D3 with U.
Mhm.
It contains three terms. You understand? Just a binomial, but the highest term on D disappears. So please try to.
What do you mean by three terms? In the commutator?
Yeah, because two of them
Is it-
cancel.
Yes, it
Yeah.
is equal U D3 plus 3 U prime D2
Yes.
plus 3 U2 prime D plus U. Okay?
Yeah, it's the same idea.
And this disappears.
Yeah, okay.
Mm.
Yeah, it's the same.
Mhm.
So this guy.
Uh-huh.
Mhm.
And these terms cancel.
Yeah, this terms comes.
Mm.
This first one. Second one should be. Then
Mhm.
I already computed this time. Something like
You have to put this D to the right.
yes, but I already computed this term, but I don't remember the
Ah,
result.
okay.
Do you have the?
I think
Yeah, it should be like. Same idea. So we have the first one.
I think it's minus UXX D and 2UX D squared.
What?
Minus UXX D
Uh-huh.
and 2UX minus minus 2UX.
Here plus, but in the commutator is minus.
Yeah, it's
Uh-huh.
yeah.
D squared. That's all because the
Yeah, but there's also another term.
No,
the one
no, no, no.
cancel each
No, no.
other.
d2u is u d2 plus 2u prime d plus u2 prime.
Yes.
So you always has a binomial.
Ik doe weer de commentator.
Yeah.
Nou, de...
Yes, now you have to put this here.
Yeah. Because I have to multiply by d.
Yes, but here is d, first power.
No, I'm putting this, not this.
Okay,
It's the same.
okay. Yes, but it is here the first power.
No.
This is strange. This is strange.
No. This is not 2. This is 2.
Yes.
This is times first
Yeah.
power. Yeah. Okay.
Mm-hmm. Discrete. Yeah. Yeah. Very good. And yes. Yes. Okay.
So,
And what else?
so the only terms that you have would be this term.
I think there is such terminals.
Yeah, there's also this term.
Mm-hmm.
We need to consider. Okay, we did this with this.
Yes. You calculate this, and now you have to calculate this.
Yeah, but we also have to calculate this and this.
Yeah. Yes.
Yeah,
Yes. Yes.
and
Yes.
this and this.
So there are many terms. I think we have to stop here.
Yeah.
But you understand the principle.
Yeah.
I'm not sure about this 7/4, but principally it is correct. So we stop here. I'd like to thank you for the participation. I hope you enjoyed some geometrical aspects of the theory of integrable systems, and I think it's very important to see these geometrical and algebraic structures in integrable system. That was the aim of our course. Thank you very much. Good continuation. See you next week.